Cool, so hello everyone. Welcome to the second edition of the WebAssembly workshop. I'm Conrad. I am one of the chairs of the WebAssembly standards body, but I'm here today with my academic hat on to bring you a great selection of talks about mostly the academic side of WebAssembly. But our first invited speaker today is on the industrial side. This is Chris Fallin. He is a senior architect at F5, which is a major, would you say, web company?
Sure, yeah, we'll go with that.
That is using WebAssembly internally for a lot of things and also now pushing some of the standardization work as well. I think that's fair to say. Okay, so Chris, take it away.
Awesome. Yeah, thank you, Conrad. So if we can get my slides. Yep, okay. Cool. So, all right. My name is Chris Fallin. So good morning, everyone. As Conrad said, I'm a senior architect at F5, where I work on many things related to WebAssembly. I'll be giving a talk today about full stack correctness in Wasm. So this is kind of a potpourri, a collection of different sorts of correctness, formal verification stuff that I've worked on over the last few years. So let's talk about WebAssembly, right? If you ask anyone what is WebAssembly, it is a secure sandbox. That's maybe its most salient, interesting, distinct property. So if I go to webassembly.org and I look at the homepage, I see this bullet point that says WebAssembly is safe. Right, so WebAssembly is a memory-safe sandbox execution environment. Switching gears a bit, if I go to the press release that announced the creation of the Bytecode Alliance, which is a consortium of companies in industry, including my employer, that are working on Wasmtime and other Wasm technologies, this press release says that Wasm is secure by default, encapsulated by default, has memory isolation between two modules. Right, so this is the really key core selling point. In fact, if I look at the press release and count words, I see that the word secure is used 12 times. So really secure. Finally, if I look at the headline for Wasmtime, which is the WebAssembly virtual machine that I work on in industry, we describe it right in the title as fast and secure, strongly focused on correctness and security. And then if I take a random article from industry, or from the industry press, and see how it describes WebAssembly, it offers secure development through sandboxing. I'm just going to pull a few quotes here. It's very secure. It uses sandbox memory. Incredibly more secure as a starting point for development, right? So let's focus on that a little bit. When I see that, I get worried, right? So like this is a great selling point if you think of WebAssembly as a building block and you are building systems on top of it. It is a great promise. But from the point of view of the people actually implementing the technology, it's actually an obligation, right? And it's a fairly scary one because there's kind of not that much in between, the sandbox boundary and some really serious, security implications. So let's talk about CVEs. Show of hands, who in this room has ever written code that's caused a CVE before? Okay, a few people. So yeah, small club. I hope you don't ever join it. This was one of my two. So about 4 years ago, it was a beautiful morning in California where I live. And I see this message in work Slack channel. Someone says, the daemon keeps seg faulting. This is the daemon that runs WebAssembly on our production servers. And for context, this never happens. The daemon is written in Rust, a memory-safe language. It's very carefully tested. Seg faults just never happen. And faults were coming from inside the Wasm code, right? So it wasn't a problem with other infrastructure. We narrowed it down to the actual JIT code that our Wasm VM was producing. So one of my coworkers says the fatal words, "I'm calling an incident," and we spun up the whole process. And this day got pretty exciting pretty quickly. And so the summary is that this was actually a miscompilation in Cranelift, which is the JIT backend for Wasmtime, that could cause a Wasm instance to be able to access memory outside of its sandbox. And so this is kind of pretty terrifying. So I'm going to actually walk through how this works because it's good background for what I'm going to be talking about in a little bit. So just as context, when you run WebAssembly on a Wasm32 on a 64-bit host, typically the way that you do this for performance reasons is that you reserve 4 gigabytes of virtual address space, and you compile the Wasm so that its accesses to Wasm memory are just offsets from the base. This allows us to catch out-of-bounds accesses with page faults rather than explicit bounds checks, which is a nice performance boon. And so in particular, in a system where you have a bunch of Wasm instances running, you'll have a whole bunch of these linear memories, 4 gigabyte regions in a single host address space. So let's look at how a single Wasm i32 load instruction is compiled. I'll show the compiler IR first, and then I'll go through some x86 code. So this is just an example here where we might have some arbitrary Wasm load, and so we have the base address that's already loaded from some virtual machine data structure. That's v0, that's an i64, that's a pointer and host address space. And then we have v1, which is some arbitrary Wasm value, i32. And so we'll extend it to 64 bits, we'll add it to the base, and we'll do the load. Right, so that seems fairly straightforward. We're just accessing an offset from a base, just like an array access. When it's compiled to x86, it might look something like the following. So say we already have the base in RDI. This is an x86 register. We'll have some instruction. Let's just say, for the example, that it's an add that produces the i32 in Wasm. So that's the add ECX from something. So that's our actual Wasm-guest address. And then we'll add it to the base, and we'll do the offset, and we'll do the load from the offset. And so an interesting semantic detail here of the x86 instruction set, when it was extended to 64 bits, is that writes to the 32-bit name for a register, so ECX rather than RCX, actually implicitly zero extend to 64 bits. And this is nice for a number of reasons, but one thing that it gives us is that we can actually elide this zero extend operator. Right? So we can know that, okay, this value happened to be produced by a write to a 32-bit register. It was automatically zero extended, so I can just add that directly to the base. Okay, so that's the code that we have. One other thing to know about the way that we produce code is that we're an optimizing compiler, which means that we don't produce the instructions directly. We actually produce virtual register code and then run register allocation. So we don't actually name the registers. We just have register 0, register 1, whatever, and then the register allocator assigns actual registers to those names. And the register allocator is allowed to insert spills and reloads between any two instructions. And it might need this because we might have more live values than we have registers. It needs to move values around to prepare for any instruction. And so you might actually spill and reload this ECX value. So that's fine. That preserves semantics, right? We write it to some slot in memory. We load it back. Everything is fine. However, we also might want another optimization, which is that when we compile code down to machine code, we have the IR type. So we might have a 32 or 64-bit value or a float 32. The register that it lives in might be wider than that value, right? So an example could be that F32 actually lives in an XMM register, which is 128 bits wide. So you might not want to spill and reload that entire datum. You might actually just want to have the narrow value spilled and reloaded. So rather than RCX, we might just spill and reload ECX. You might start to be seeing where this is going. Okay, so to start to put the pieces together, we have an optimization where we elide 32 to 64-bit zero extends because they happen for free on x86. We also have an optimization where we spill only the actual value width. And so really the core bug here is already on the screen, which is that we are using the upper bits of the register when they're technically undefined. So we map narrow values to wider machine registers by saying the upper bits are undefined. So we did not reflect that in the IR type. Right? But then there's one other thing that's sort of the icing on the cake that made this a really exciting CVE. So if we just had this code, it would actually still be fine. We would have gotten lucky because the load back into ECX would have still zero extended. But when we wrote the code, when I wrote the code, I should say, it's my fault. For some reason, I still don't know why, maybe a copy-paste mistake, I did a sign extending load rather than a normal load. And so the effect of this is that we would spill a value, we would load it back, the upper bits would turn from zero extended to sign extended. And that happened in the middle of the sequence that assumed that it was still zero extended. And so the effect of this is if you had a Wasm address above 2 gigabytes, it would actually become, negative. So 3 becomes -1 gigabyte, which is really exciting when you have a host memory layout that looks like this. One guest gets to access another guest memory. So contrary to that meme, this is actually not fine, right? Okay, so the aftermath of this was kind of as you would expect. We did an emergency version bump. We did a patch release. This is actually kind of a good forcing function for our CVE process in Bytecode Alliance. We hadn't really developed a lot of the details of this, so we're much better now. Of course, we hope that it never happens again, and so we started asking questions, how can we ensure this never happens again? I'll put an asterisk on the word again, because it turns out it did happen again. This one was also my fault. And so I won't go through the details of this one. Basically, we flipped a uextend and a left shift, and you could control some bits above 32. It was not good. Right? And so like this is great for verification researchers, but the fact is that we're human, and so this is going to keep happening, and so we need to ask, like, can we do better? Are there ways to do better? So actually, one thing I want to talk about is why are we even in this mess in the first place? In particular, why do we trust the compiler, right? So we have pretty nice abstractions like virtual machines or even processes on a multi-processing operating system that are very strong and well-tested isolation boundaries. So why not just use those? So it actually goes back to this paper from SOSP 93, which introduced SFI, software fault isolation. And so the idea here is that in some circumstances, when you have a whole bunch of distinct trust domains that want to rapidly either call each other directly, so actually interact, or you're just time slicing between them, you actually don't want to pay the context switch overhead if you're using processes, for example, or separate address spaces. So it actually makes sense to pay the slight overhead of the instrumentation handled by the compiler in order to do the isolation compiled in software. And this is a system design trade-off, right? And so you might say, okay, well, you know, that's kind of a niche thing. You have a whole bunch of Wasm instances in one process. But actually, this is kind of essential for many workloads, not just server-side, where we have very dense multi-tenant with many different trust domains in one process, but at the browser as well, right? Wants fast Wasm to JS interaction. And so when Wasm calls JS and JS calls Wasm, that's also kind of crossing this SFI boundary. And so this is actually, I would argue, one of Wasm's secret superpowers. And actually, there's a blog post by Lynn Clark and the Bytecode Alliance blog called, that describes this as nanoprocesses. It's like a really powerful building block to have these extremely tiny virtual or trust domains, virtual machines essentially, that you can put inside of a process. But in order to have them, we have to trust the compiler, right? And so that's the problem we need to work on. Okay, so how do we write a correct compiler? Well, we do a lot to try to ensure correctness. So I'll just walk through, like, you know, we do all best practices. We do differential fuzzing against the Wasm spec, against different Wasm implementations, V8, Wasm-i. We do actually symbolic translation validation of register allocation and fuzz with that. If I have time, I'll talk a little bit about that. We do chaos testing, so we like perturb the compiler and make it do different semantically valid but weird things. We also let the compiler backend, Cranelift, be used as a Rust backend. So that's kind of trial by fire, compile the entire world in Rust and you find bugs. But somehow we still find these CVEs. And if I extrapolate from these 2 data points, and I have a line, I can say that they happen once every other year, right? So that's still not that great if this is if this is the only thing between us and a data breach. So I would simply prove the compiler correct, right? How hard could it be? So actually, that's kind of what I did, or what I'm trying to do, I should say. I have not, and by any means achieved this. So let me outline what the anti-goal is first. So there are actually 2 well-known projects, at least. There may be others that I'm not aware of, which is to prove an entire compiler correct from end to end ahead of time for all inputs, right? So there's CompCert for C, there's CakeML for ML, and these are extremely impressive projects. Don't get me wrong. But they were started from the beginning, at least as far as I understand, with the goal of being a verified compiler. And that sort of trickles through all of the other decisions that they make at an engineering level. And so they're engineered from scratch. We have 200,000 lines of existing code that we're not going to rewrite. They also limit, to some degree, the optimizations that they do because they have to be proven correct, right? There are some code transforms that we as humans can reason informally about or just know work, but are quite hard to do a machine-checked proof for. And then finally, it's an enormous manual effort. We can't afford an engineer century as, you know, a 5-person open source project. So okay, let's narrow scope a little bit. And there are maybe 2 ways we can do that. We could verify a part of our compiler completely for all inputs, right? So let's pick a phase, maybe instruction selection. Or we could verify certain limited properties of our compiler end to end. And so I'll actually talk about both. For the first time, I'm going to crib the work that my collaborators and first authors did much more than me, but I'm going to talk about work that we published this past year at ASP+, just very briefly. And then the second part, I'm going to talk about proof-carrying code, which is kind of ongoing work. So we're going to talk about that, and then if I have time, which I might not, I'll talk about guest code correctness as well. Let's talk about instruction lowering. What is instruction lowering? So in a compiler backend, you have an IR, and you want to produce machine code. Maybe the most interesting part of that mapping is that you actually pick the machine instructions that correspond to the IR opcodes or the IR instructions. And this is a fairly intricate problem that has a lot of domain knowledge encoded, and you want it to be good because you want good instruction selection. You want to produce good code. And so there are a lot of like clever tricks that end up happening that mean that this is very fertile ground for bugs. And so about 4 years ago, I designed a DSL that we call IL that we use in Cranelift that is used for us to express the lowering rules from the IR to machine code. And right at the very beginning, I actually put this paragraph in this RFC that I wrote describing the design, where I was thinking about verification, and I didn't really know exactly how it would work, but I was at least signposting, okay, we probably want this at some point. And so it's a term rewriting system, and so I sort of designed it to be hopefully amenable to that. A few months after that, I wrote another RFC in Bytecode Alliance. I was tech lead of Cranelift at the time, so I wrote a roadmap for the next year. And I said in the next year, we should attempt to find some concrete ways to do formal verification. A few weeks later, I got emails separately from two academics, Alexa Van Haddam and Fraser Brown, who are both my excellent collaborators now. And so they both wanted to work on this. And so we started up a collaboration. And it turned into this in S+, right? So that was pretty cool. So I'm going to describe sort of how it works. Let me show you a rule in IL. So this is a simplified example of like the simplest possible instruction selection case that you could have, which is that we have an IR opcode, rotate right, rotor, that maps directly to an AR64 instruction that's also called rotor. So super easy. All we have to do is map the opcode to one instruction. And so the way that we might verify this, you could imagine, if we're using an SMT solver like Z3, is that we would have a theory bit vectors formula for the semantics on the left-hand side and the right-hand side. And we would then just ask the solver, are they equivalent? Or if not, give us a counterexample. So that's actually kind of a high-level sketch of what we did. But there's a lot more that you need to do to make this work. And the reason that it gets a little more interesting is that in a real system, we don't just have sort of this cartoon term rewriting where we go directly from the terms on the input to the terms on the output side. We actually have a lot of what we call helper terms. So here I'm showing slightly more detail, still a lot elided. But we have this helper term that we call hasType. It's actually a virtual term, so it calls into Rust. It doesn't actually exist in memory. And if you expand the call graph, or the rewriting graph, I guess, there are like a bunch of levels. I won't go through all the details here. Similarly, on the right-hand side, there are a whole bunch of levels to the term rewriting, down to something we call put-in-reg, which maps an SSA value to a machine register. And so it's actually not as simple as just saying, here are the semantics here are the semantics here, prove them equal. We have a whole bunch of terms, right? And so what we ended up doing, and the thing actually I didn't mention is that we don't ever materialize these terms in memory, so it's not actually a rewriting system from a concrete tree of terms you can dump here and here. These terms actually bottom out in FFI into the rest of the compiler, which is written in Rust. So they're virtual terms. And so at some level, we have to sort of like draw a boundary and say, we have a reasonable spec at this interface. This is actually the IR interface, and the rest is just glue that we're going to ignore for now. And so what we did is we drew that boundary on both sides, something that looked like the IR, something that looked like the machine instructions. And then we attached these spec forms to every helper term, basically. And the way they work is that they provide certain SMT formulas, given that certain formulas are true, right? So it's an implication. It's precondition, postcondition, standard verification stuff. And there's a lot more that actually is needed to make this work. That I won't talk about for time reasons. We have to handle type polymorphism. The rules work for different widths. There's a lot of stuff that makes that tractable. But the upshot is that it actually does find real bugs. So it hasn't found a CVE yet. I hope it never does. There's kind of a conflict of interest here. I don't want to write CVEs, but then I do for this project. But it has reproduced the CVEs that we found. And it's found some other interesting edge cases that we don't consider CVEs, but are still compiler bugs, especially with narrow values, end up being pretty tricky. And so there are ongoing discussions. The thing I want to highlight here is that this is not just a once and done academic project that verifies a snapshot. There are ongoing discussions in how to make this scalable in terms of runtime, and then easy to use, such that we can actually incorporate it into our CI. And have it part of our normal developer workflow. So the holy grail, the end goal, is that we have our open source project on GitHub, and someone does a PR to add a new instruction selection rule, and we can actually know right then and there if the SMT solver likes it or hates it, and if it hates it, how do we prove it correct, or how do we fix the bug? and give us a counterexample, et cetera, right? So that'd be great. Okay, but can we verify something end-to-end? So here's a high-level view of the Cranelift compiler pipeline. So we start with Wasm bytecode. There's a translator to CLIF, the Cranelift intermediate format, which is our IR. There's an optimizer that goes CLIF to CLIF. Then instruction selection, which is what I just talked about, that goes to virtual register code, vcode. And then there's machine code at the back end. So we verified, kind of, it's in progress, the instruction selector. I'll talk more about the register allocator later. We do translation validation there. But what about the other two phases? Those are large bodies of code, especially the optimizer also has a lot of cleverness embodied in it. And then there are also integration and glue bugs, right? So there's the thing where you verify every individual phase, but the assumptions that they make at the boundaries are not exactly lined up. For example, yes?
Yes. So the bug you showed earlier was an optimization on the assembly level, right?
Yes.
So where does that fit into this pipeline?
So that would actually have to do with the way that the register allocator is integrated. Well, one of two things. It's either the move sign extend is at the register allocator level. It's also the instruction lowering that assume the wider type is at the instruction selection level. So we do, in principle, have the pieces that we would need to resolve that. For practical reasons, we actually verified AR64, not x86, so we haven't actually reproduced the 2021 CVE yet. But in principle, we could. Yeah.
Okay, thanks.
Yep. Okay. So yeah. So what about integration glue bugs? What can we get something that's actually end to end and that we actually feel good about? So proving the entire compiler correct is hard, right? C compcert, C CakeML. Can we actually prove something much narrower, namely that all memory accesses in the machine code are to valid data structures, so are to either the sandboxed memory or are to VM, like VM context structures. And the way we might do this is we might build an independent checker that operates on the machine code after the compiler is done, right? So the compiler is not trusted at all. It's not part of the trusted computing base. We're just verifying that its output conforms with our expectations. It turns out this has also been done. This was some of my collaborators, but before my time, I was not involved in this work. This is VeriWasm, right? So that Russian there means trust but verify. So trust but verify, SFI safety. And it actually works on Cranelift, which cool. So maybe we have something we can use. Unfortunately, it was written to work on Cranelift, but another Wasm runtime that uses Cranelift, which is now end-of-lifed, called Lucid. And so at the time, that was sort of one of the leading options, and so that made sense, but now Wasmtime has kind of taken over. And then it also operated on a much older version of Cranelift, which was sort of poorly optimizing, which makes the problem easier for the verifier, but anyway, so we'll talk more about that. Okay, so VeriWasm actually verifies multiple properties, stack safety, a bunch of other stuff. We'll talk about the Wasm heap here. I want to give the key idea here, and then we'll sort of talk about what I think we're going to do to extend it. And so the key idea with VeriWasm is that it's an abstract interpretation. They define a lattice that's focused on essentially what the memory sandboxing code does. So there are different states that represent the different pieces that have to come together. So here we have some code that has a heap base in some register. We have some I32, and then we're going to add the base to the add the I32 to the base, and then access the offset. So you can imagine that we would have a lattice value that in our abstract interpretation that represents the heap base. We might have another that represents a bounded 4 GB value, right? So this is a value that's been 0 extended from 32 to 64, and is from 0 to U32 max. And then we could define operators over our abstract domain, such as addition, that would take heap base plus bounded 4 GB and would tell you that that's a valid heap address. So if you load from that, that's a valid load. And so you can imagine building a checker in this way. And it would work, and in fact it did. That was the 2021 paper. So actually, after our CVE in April 2021, around May, I took a look at this and wondered, could we update it to work on modern Cranelift and Wasmtime? And so I actually did do an update to Wasmtime, but for a very limited domain, so one memory only, no dynamic bounds checking. We found that I had about 30% compile time overhead, which for an academic work is actually fantastic, right? But at the time at my employer, we had very limited control plane resources, and we actually could not afford that. And so we opted not to deploy it. So it just kind of was shelved and sat there. And then the 2023 CVE came along, and I started thinking again, like, okay, we really need this. It would be really great if we could find a way to make this work. And at the same time, Cranelift and Wasmtime had both advanced significantly in the features they supported and the optimization strength. And so there was a question of how are we going to actually make it work for more complicated code. that is more optimized. So let me talk about what some of the differences are, and I'll actually talk about multiple memories and tables. So Lucid actually, the earlier Wasm VM that Vera Wasm worked on, had a very simple memory model. Its data structure was basically a single heap in one direction, and VM context, so Wasm globals and some other miscellaneous state, in the other direction, from a single pointer. And that single pointer was held in a pinned register. It was always the same register in machine code. And so that actually is what enabled that lattice-based approach to work fairly well, is that the code was of a fairly restricted shape. On the other hand, Wasmtime is a little more flexible. So first of all, we do register allocations. We don't have a single register that's pinned. We allow the register allocator to move the pointer to the VM context around, spill it, reload it, so already we see we're going to have to track that movement. We also support multiple memories, and we support different kinds of memories. So there's a level of interaction with memory descriptors. Some of these memories are not bounds checked, some of them are. And we have shared versus non-shared memories for Wasm threads. All sorts of interesting edge cases where we have optimizations that produce different machine code that we would have to handle in this analyzer. And also the optimizer got better. Yeah, that created a lot of problems. So let me talk about what we want in the perfect verifier. We want linear time and space verification, and this is actually something that Wasm itself, core Wasm, focuses on as well, right? When you load a Wasm module, you want to know that you have, you don't have the possibility of the denial of service with an untrusted Wasm module, causing the verifier to run for example, quadratic time. So let me talk about how that doesn't happen if we do sort of a naive approach. So I'm showing some machine code here with 3 different accesses to 3 different memories, a static memory and 2 bounds checked memories. And I'll walk through which part is which. So first we compute some arbitrary I32. And then this move RBX, this load into RBX, is a load from a 4 GB memory that's statically bounds checked. So there's no bounds check in the machine code, it's just the virtual memory tricks. And then we have a dynamically bounds checked memory where we compare RAX, the address, to R9, which is some other memory bound that we've loaded before. And this is spectre safe. We deal with spectre mitigation, so this is a conditional move rather than branch. We basically move 0 in if it's out of bounds, and we do that again, right? And so we actually have 3 different conditions on RAX here. If we were to try to describe this in some value in a lattice, we might have to have some expression like this. It's less than 4 GB statically. It's also less than R9. It's also less than R11. And so you can see how if the optimizer starts to merge together these different accesses and merge the pieces together, we end up getting a very complicated analysis domain where we're deriving a whole bunch of facts that are unnecessarily merged together. And this can cause quadratic behavior fairly trivially, right? And so we're in an environment where we don't trust the user input. We're trying to compile and run the code, but we don't trust the producer of the code. And so we can't have this. This is a denial of service vector. And then there's also the complexity here where we have 2 separate pieces that have to be combined later. So we have the compare and the C-move, and you play a lot of tricks getting the lattice just right, and it ends up being very brittle. We also want this to be portable, so we have x86 and ARM. We don't want to have too much that's architecture specific. Basically, we just want semantic descriptions of what the instructions are, and that's it. We want to be able to keep it up to date, right? So adding optimization shouldn't be too hard. And we want to prove the safety of all loads and stores. And then we want it to be fast enough to run in production, right? So just a few requirements. How hard could this be? Okay, so because this is a workshop talk, I'll tell you this is a work in progress. I've tried 4 different approaches. I'm on my 5th. I think number 5 is going to be the lucky one. But what does work is that this does actually work for multiple static memories in modern Wasmtime and Cranelift. Over Wasmtime data structures and all Cranelift optimizations turned on, and it has 1% compile time overhead, which is pretty fantastic. So it's still kind of it needs to be fuzzed, it needs to be productionized a little more, but at some point this year, I want to try to get this turned on. And so, yeah, I won't talk about the different approaches I took that didn't work. Right, okay, so what is the key idea here? It's proof-carrying code. So this, again, is an old paper, actually, from Popple in '97. And the key idea with proof-carrying code is that the compiler itself will give you a proof that says this is why the code satisfies certain properties, right? So instead of having this analysis that has to derive all possible facts and then try to put them together, PCC will say, I'm giving you exactly the breadcrumbs that you need to follow, and the checking is much cheaper than the from-scratch analysis. So think of it kind of like typed assembly, which is a related work. And so I'm just going to show you, for time reasons, I'm just going to show you a very brief overview of how this works. So this is IR from Cranelift. This is Cliff. And the important and interesting things to note here are the bang expressions. So I have GVs, which are global values. These describe the VM data structure. So VM context, field on the VM context. And then below we have the SSA, IR, and we have values that are basically loading the memory base and then adding the base, or adding the offset to it and then doing a load. So the bangs basically describe what we call facts in the PCC system, but you could think of them as types as well. And so basically we say that the first argument is actually a pointer to MT0, which is a memory type, and it's offset 0. So the two numbers are min and max offset. We have a range. So this is an absolute offset of 0 into something that is memory type 0. And memory type 0 is a struct. And we're not going to tell you everything about the struct because we don't actually need to use this for compilation. We only need to tell you what you need to know to verify the facts that we give you. And so the struct here is basically saying that it's 88 bytes, so we allow any load within the first 88 bytes offset. And then we have a field at offset 80 that has another fact attached to it. So if we do a load from that field, we get to verify and use that fact. And so we verify that when we do the loads. We also have facts that describe ranges, right? So if we have a uextend from 32 to 64, we know that that value is going to be between 0 and U32 max minus 1 inclusive. And so that's going to verify. And then we can basically define abstract domain add operations on these facts, just like we did in the lattice for VeriWasm, and say that if we have a memory type 1 offset 0, and add offset 0 through U32 max minus 1, we can add the ranges, and know that this is a pointer to memory type 1 somewhere in that offset range. And then we know that MT1 is a memory that has that valid amount of space, right? So it's a 6 gigabyte reserved virtual memory space, so allow any load or store within that range. And so then when we have the checked flag on a load, we actually check that the address has the necessary fact, and we reject this code if it doesn't. So there's some stuff with dynamic bounds that actually I won't go too much into. The only thing I'm going to say is that the key idea that I have that I want to pursue is basically taking the exploded pieces that the optimizer has too much fun with and having a single opcode that goes all the way through to machine code as a pseudo instruction that encapsulates the entire dynamic bound check sequence. The key aspect here is that this gives us a single point on which we can hang the type, and it gives us a unique identity, a different SSA value that lets us check that separately from anything else the optimizer might combine it with. Okay, I'm going to skip regallic. Basically, we just do symbolic verification that the regallic result is equivalent, and we fuzz with this. The thing I'll say about it is that it's extremely effective, and we actually haven't had a regallic bug in production in 3 years because we do this fuzzing with symbolic checking. And then the last thing I'll talk about is inside the sandbox, right? So we've talked about sandbox security. We have formal verification, translation validation, great. Right, so that boundary is secure, but what about inside? And so, what is the threat model? Let's ask this question here. If we care about keeping our hosts safe, then that's all we need. But if we care about code attempting to subvert logic inside the guest, which we might if it's server-side WASM, for example, doing authorization checks, then we actually care about correctness of the language implementation inside the guest as well. And so we need a correct language implementation. One example of how this might come up is you have Cloud Bleed, which was a bug about 7 years ago. Cloudflare was leaking undefined memory from one connection to another, really, really bad. And so cross-request isolation is actually important, and we use the WASM boundary for that. We have separate sandboxes. But even within a single request, we might want correctness. And so how do we build correct JavaScript? Step one is use someone else's JavaScript. And so I'm talking about JavaScript as a guest here, but the same ideas would be applicable to other languages as well. So we started with SpiderMonkey, which is the JavaScript runtime produced for Firefox. It's fuzzed, it's got a security team, it's quite good. And then step two is avoid the JIT compiler. Because most of the CVEs that happen in language runtimes happen inside of JIT compiled code with things like type confusion bugs. Don't you want performance? Yes, we'll get there. Right, so, and that's all we can run on Wasm today anyway. So basically, we can only compile an interpreter to Wasm. We don't have a JIT backend for Wasm. And so sort of the thing I want to say about interpreters is that interpreters are really easy to write and really easy to get right as compared to JITs. This should be uncontroversial, I think. JITs are an order of magnitude more complicated. You're sort of working indirectly rather than directly. The other nice thing about an interpreter is that it's portable. So if I'm developing on Wasm, I have a much worse environment still today than I do on native. One tool that I really like to use is RR, the reversible debugger. It's fantastic for finding bugs. It only works on native Intel and some ARM chips. Right? So on native x86, I have R, perf, GDB, Valgrind, all the things. Wasmtime GDB kind of works, but like kind of not, and I often get assertion failures. So I'd rather develop my interpreter natively and then just compile it for Wasm. So the thing that we did, and I will go very fast here because I have 0 minutes left, is that we have a single source of truth, an interpreter, and we do partial evaluation to produce a compiler from that interpreter. You can see another talk that I've given to see how this works. And we get 2 to 3x speedups. This is real. It's deployed. And the thing that's nice about this is that we're developing a JIT from first principles, right? So basically the idea is that we want to have the semantics only in the interpreter, and then we want to have validated tools that give us the JIT compiler for free from that. And we have some ideas on how to do other optimizations. But yeah, limited formal methods can work. Meta compilers can work. And I think there's a lot more to do here. And Wasm has set an excellent precedent with explicit semantics. That's all I had to say. So thank you, and any questions? Deepti? Yeah.
Just very quickly, as we're having questions, could we have the next speaker just set up if you move your mic? Okay, I'll check in with the people.
Any other questions?
I have maybe 3 questions, and I'll go through them really quickly.
Yeah.
When you had a spec boundary, what are all the features you're testing in that spec boundary? Because we've had a few CVEs, but they're all in this overflowing stacks or type confusion, that sort of space. And I was wondering if you expect them or how you're thinking about them.
Yeah, so at the machine code level, but at the virtual register machine code level, pre-regallic. So there's a separate regallic thing that we do. There's still potential for still potential for issues in the glue. So that's why we have the end-to-end validation as well. Yeah.
Okay. And I don't know if you mentioned quite a bit about just bounce checking and like memory safety, but maybe control flow. Could you speak a little bit more in terms of control flow and how you're validating that that's safe?
So the short answer is that Cranelift is not smart with control flow. Basic blocks remain basic blocks. We don't have any optimizations that change that. So we haven't put a lot of effort into that. If and when we do, then I'll have to think more.
I'll find you later.
Okay, thanks.
Yeah, so you mentioned quickly that you also add some code to protect against speculative side channel attacks.
Yeah.
Is that a worry for you? And would you also like to verify some of that?
It is a worry. So we do very basic mitigations. We do C moves rather than branches, which protects Spectre v1, not other variants, right? I think more would be nice. So yeah, I'd be happy to talk offline if you have more ideas.
Thanks.
We have time for a couple more questions.
Yeah, maybe this is too much in the woods, but I was a bit oh no, we don't have the slides anymore. This will be hard. I was a bit confused by what you showed, the logic that you showed when you did this addition on the pointers that there was a pointer to a particular thing at offset 0.
Yep.
And then you added an arbitrary number to it. Because the type had some assumptions itself about a certain thing inside its offset. Like at offset 80, there's another pointer or something. If I offset my pointer by a bunch, that doesn't translate. Right, like I have something at offset 0 that has at offset 0 plus 80 the right thing. Now I add 100 to it. Now at 100 plus 80, how do I know I have that thing still?
So the semantics are that the memory. So the fact on the pointer says that I am pointing to this type at this offset, and so if I'm at this type at this offset 80, for example, and I do a load with additional load offset 0, then I know that I'm accessing the field at offset 80. So we don't translate the type. The type is always a fixed layout with fixed offsets. We track the offset of the pointer within that type, if that makes sense.
So I mean, maybe you just couldn't see because it was hidden behind the table, but the fact that you had on the added up pointer did no longer have the empty 0, or did it still have the empty 0?
So I think the example I showed never actually added anything to the VM context pointer. We loaded from it, and we got another pointer. And that pointer was another type that described the memory that it's pointing to. I can find you offline. And we can
Yeah,
go
I
through it
guess
more
that
if you
was
want.
just a bit too fast for me then. Okay, thanks.
Yeah.
All right, thanks again
Thanks.
to Chris.